Join the happiness. Admissions open. SRM Ishwari Engineering College.
Good evening, sir. Sivaguru, sir, is it audible?
Hi, good evening, ma'am. Yes,
Yeah,
I can hear.
Thanks.
Good evening, sir.
Good evening, sir.
Good evening, ma'am. Good evening, sirs. Good evening, everyone.
We'll start the session by 4 o'clock, sir. We'll just wait for a few more minutes.
Sure.
Yeah.
Good evening, sir. Sorry, sir. Shall we start now?
Yes, ma'am. Yes, ma'am. We will start now. Hindu,
Yes. Good evening to Sir, shall we start?
Yes, ma'am.
Good evening to one and all present here. Esteemed Chairman, Ramapuram and Trichy campuses, respected Co-Chairman, Principal, Vice Principal, distinguished Chief Guest, Head of Department, and dear colleagues and faculty member. I extend a warm welcome to all at the third day session on International Faculty Development Program, Recent Innovation and Emerging Advances in Electrical Engineering, organized by the Department of Electrical Electronics Engineering, Ishwari Engineering College. I now request Dr. P. Maris Kumar, Associate Professor, EEE Department, to introduce our Honorable Chief Guest, Sivaguru Paramasivam, Energy Storage Expert, working in Abu Dhabi Future Energy System.
Thank you, ma'am. Thank you. Good evening to one and all present here. I taken the immense pleasure in introducing our speaker of the session, Dr. Sivaguru Paramasivam. He is an expert in renewable and energy storage systems. As an electrical and electronics engineer, he has extensive experience in technical, commercial, and business functions in renewable energy like solar, wind, battery energy storage, industrial, automation, and control systems. He had led and worked on various roles in like product development, system engineering, applications, project management, and business development in leading MNCs for the last 15 years. Some of his technical contributions include design power electronic products for grid-connected power conversion systems, integrated control systems on application layers, and develop energy management algorithms for large-scale hybrid projects. On business and commercial functions, he had executed projects through cost to society, environmental and economic impacts of clean energy technologies for grid planning, integrated resource planning for energy infrastructure, financial analysis of demand management programs, concept to completion models, etc. His experience is global, from small island in the Pacific, isolated traffic diesel grids in Africa, hot deserts in the Middle East, larger island utilities in the Caribbean to mainland utility networks in North American and Europe. An accomplished speaker, he has led training workshop on battery energy storage systems, integrating renewables into electrical grids and microgrid readiness, etc. His previous associations were with Delta Electronics and Parker Hewlett Corporation. Thank you, sir.
Thank you, sir. I request our Chief Guest, Sivaguru Paramasivam, Energy Storage Expert, to deliver a talk on application of power electronics and machine learning to renewable energy.
All right. Thank you, sir, for the introduction, and good evening, everyone. Thank you, SRM Management, for organizing this and giving me the opportunity. And on top of everything, I thank you, all the participants who are here. So I hope all are keeping well and safe with all your loved ones. Everyone is safe in these challenging times. So with this, I will display my screen. To start the session. Could someone confirm if you can see my screen, please?
Yes, sir, we could see your screen.
Thank you. So today's topic is about the application of power electronics and machine learning in the renewable energies. So what I'm going to do, I'm not going to touch more on the academics because you are all the expert in that, but I'm going to take you through the market, the global scenarios, and the application of the real life applications of real life power electronic equipments, and also how it's used in the overall renewable energy market, and what are all the future trends it's going to be like. So my first slide is about giving a global overview of the renewable energy market. So why we are all hearing about the renewable energy for a long time now. So you can see the reason by yourself. Just by seeing the graph to the right hand side, you can see that the black one is the coal And starting from 1980s to now, you can see the coal power is reducing. The installation of the coal power is reducing. And you can also see that the solar power, which is marked in the yellow color, is increasing a lot. And similarly, you can see the other renewables like wind, like both onshore and offshore winds are in a upper scale, but the traditional fossil fuels and carbon generating energy systems are retiring. So that's one global trend that's happening in the energy market. So, and you can also see that most of the governments, including the developed countries and developing countries, are making out or working out a plan that they say that by 2050, which is like in 30 years from now, they are going to have a net carbon zero goal, which means whatever the carbon that they are going to emit to the environment, somehow or the other, they are going to compensate that by providing a cleaner and greener energy in whatever mix we are going to use that. In similar ways, we hear a lot of policies, including the Paris climate policy, which is favoring the renewable energies, and a very ambitious plan of 5 terawatts in 2040 is being planned. And at the bottom, you can see the major countries like China. They already have like 9% of their energy mix coming from the renewables. USA, particularly in California, they have more than 50% of their power coming from the renewables. In India, we have already achieved 35% in 2019. In Germany, that's more than 50%. In France, 23%. Australia, 24%, and UK, 40%. So, which means the renewable energy is highly accepted in the whole world, not just in one terrain, one continent, but it's broadly accepted everywhere, and it's very popular because of the reason that it's highly efficient and good for the environment. So you can also see a kind of bar chart at the bottom that shows like within all the countries, which country is leading by having huge number of renewable mix. China being the largest country, it has the highest power of renewable mix. There's a reason you can see that China is having a larger marking in the red color. And then eventually comes the United States. And third is India, which is an encouraging news for all of us. We who aspire to work in the renewable industry in the future are also going to have a huge potential in working in this market. So with this, I would like to touch upon the hybridization that's happening in our energy system. So traditionally, I hope that we have all learned that energy is generated, transmitted, distributed just from either a thermal power plant or a nuclear power plant or a hydropower plant for in a very minimal locations. But the new grid is getting transmitted, or rather is getting hybridized by adding a lot of new energy sources like the solar systems, which you all know that the photovoltaic solar power is becoming very popular. And also the hybridization is coming from another technology called energy storage and microgrids. So whatever the solar is being generated during the daytime, could only be used during the daytime, because we know that energy can be, particularly electric energy can be generated and consumed. It cannot be stored. That's what we learn in our semester 1. But thanks to the introduction of battery technologies, of course, capacitors can store the energy, but we cannot use the stored energy in a capacitor for a large application or for a long period of time. But in today's battery technology, what we also do is that within the grid connected system, we can use battery as one of the source for the complete night time. So that's why you can see the solar and storage are getting combined, and we can use this mix to receive the renewable energy throughout the day and throughout the night. And that's what I try to show here. And there is one concept that you can see that is mentioned as VPP, which is nothing but a virtual power plant. So the future is also going towards VPP, wherein that we have all the traditional and modern energy sources connected to each other, and there will be one grid control center sitting on top of them, and they will be commanding that from where the energy is generated more and from which point of the load the consumption is more, and how to compensate these energies in between, and to have a very neutral grid. So what happens is we all get a very pure power quality, and also the energy is not getting wasted anywhere. So we will not have the blackouts, grid outages anywhere. We will also not have some of the transformers getting overloaded due to the high load at some point of time. So we are trying to neutralize everything and trying to bring everything on a same network for the whole system's benefits. So this should be an interesting slide. So this shows the overall energy infrastructure solution. It might look complicated, but let me try to explain. So whatever I have marked here in the red text is all the power electronic equipments, and that's what is our topic for today. You can see the whole energy infrastructure. You can come from the top. The top layer is showing the generation and transmission distribution. The one source you can see as the power station, and the thermal power station, and you can also see the PV, which means photovoltaic solar energy, and then you can see the wind power plants. So the wind power plant. So what is a wind power plant? If you have a wind power plant, it has a wind turbine, and then it has a wind power converter, which is nothing but a huge power electronic component. And similarly, you come to the solar system, photovoltaic system. So we have huge solar panels, but the solar panels can only generate the DC source. It's only a DC source. We cannot use the DC source in our day-to-day life. So we will be using a PV inverter, which I will be covering up in the next slides in detail. But you can see the PV inverter, which is another huge part of the power electronic that we are using in the energy infrastructure. And coming to the bottom, it's all on the consumption end. You can see there is a battery container that's mentioned, and the battery container is again a DC source. The DC, we know that battery can only have a DC positive and negative, and then it's connected to a megawatt scale power conversion system, which we call as PCS, and then it goes to the factory, and that's again, that has a huge power electronics in it. And today I am sure that you all are hearing about the electric vehicles and e-mobility, things like that, which also India is having a plan to go, I think 20 to 25% of electric vehicles on road by 2030. So which means there is a huge requirement of DC chargers and AC chargers, which is going to charge your cars and vehicles, even motorbikes, and even buses, or even today we know that Ashok Leyland kind of companies have also launched electric buses. So which means the charging systems are also going to play a huge part in the network, in the energy network. So similarly, there are some small commercial and industrial PCS that's again of the same purpose, but the capacity is lower. So the purpose of showing this slide is you can realize from this slide the importance of power electronics in the whole energy network. So I will try to go to the solar systems first. You have seen a lot of energy components here, but let us go one by one. I will first start with the solar networks, solar solutions. To the left-hand side, you can see there are primarily, when we say solar power or solar system, there are three types of systems are implemented in the real life scenarios. The one is residential market, which is usually starting from 1 to 5 kilowatts or 5 to 10 kilowatts in the range, which is the power requirement is very low. So that's why there is a certain power electronic component called as micro inverters. So whatever we use in our residential applications, so what happens, you can see a PV panel here, the PV photovoltaic module, and the photovoltaic module is getting connected to a micro inverter. The DC, both the DC positive and negative are getting connected to the micro inverter, and then the micro inverter converts the DC to AC and directly provides the 230 volt grid to our loads, or it can even be connected to the grid. And at the bottom, you can see the power block of the system. You can see that the PV positive and negative is coming, and then there is an active clamp DC-DC converter. It converts the DC, it regulates the DC, and then the DC is converted to AC, and finally it's given to the load or to the grid. And there is a feedback system that is used as a control system to control the whole process. This is totally a different topology of power electronic, but when we come to the commercial application, so commercial application starts from maybe 10 kilowatts to 500 kilowatts. When we see a huge factory, or when we see a big, hospitals or banks, or even in some of our colleges, we have the rooftop solar systems. In all of them, we have multiple of the string inverters. So the string inverter typically looks like the box that I have shown here. The multiple of the solar strings are getting combined, and then it comes to the string inverter. And the string inverter, multiple of these string inverters collectively goes to the grid. You can see the topology at the bottom, which is like there is a solar panel. The solar panel goes to again a DC-DC converter, and then the DC-DC converter goes to the DC-AC converter, and then it goes to the low-pass filter. It's nothing but a filter to mitigate the harmonics, and then it's given to the grid, because we cannot pump the harmonics to the grid. The grid is having a requirement that as per the IEEE 519, it says we should have less than 3% or less than 5% of harmonics when we are connecting power electronic equipment to the grid. So why there is a harmonics generated from these kind of systems, you know very well. All these power electronics are nothing but the switches. So that, like the switches that we have in our home, when we switch on, the electricity passes. When we switch it off, it goes off. But what is the difference between that switch and the power electronic switch? This is the ultra high speed switch. So it can operate in kind of 5,000 to 6,000 hertz, kilohertz even. That's what we call a switching frequency. So with that kind of high speed switching, we get the power conversion and whatever the required profile of waveform that we need in the application. Okay, and then you can see a grid synchronization block, which means from the grid we need to tap a feedback. So whatever the voltage frequency, phase angle, and power factor, whatever is at the grid side, the inverter should also respect that, and it should be combining to the grid with the same frequency, voltage, and phase angle. Otherwise the system will not work. Otherwise the system will trip. So that's the reason we take a feedback from the grid, and then we control the power electronic switching with respect to the feedback we receive from the grid. This is the second type of solar system. And the third type of solar system is called grid scale or utility scale solar systems. And the type of inverters that we use there is central inverters. So when a central inverter will come, the minimum central inverter capacity available today in the market is 1000 kilowatt, which is 1 megawatts. And one central inverter maximum size that we have today is 3.5 megawatts. So you can imagine that one unit is just like 3 meters long and 800 mm, like 800 mm in depth, and its height is about 2 meters. So that box will give a power of 3 megawatts. When connected to the solar panels, it can inject a 3 megawatt of power continuously to the grid as per the irradiation levels. And that's having a huge chunk of power electronics again. That's what I'm trying to show it here. Let's start from the left hand side. You can see the solar panels are getting connected to this system, which is the solar system is again nothing but the DC positive and negative is connected to this inverter panel, and the inverter panel will immediately have some protection devices like surge protection, over voltage protection, over current protection. So when there is a problem in the modules, the short circuit current should not affect the power electronics or the IGBTs in the system. So we have all the protections there. And then it's coming to IGBT switch. So usually it will be a 6 pulse, 12 pulse, or 18 pulse configuration, depending upon the type of the inverter that we use. And what it does is basically the DC, which is coming from the PV, it switches and then it converts to the AC voltage. And then when we have the switching, you can see here in this case, we can see L, C, and L filter. You can see there is an inductance, and then there is another inductance in series, and to the parallel there is one capacitance. So the reason for having this kind of LCL filter is, for this kind of system there is a huge amount of harmonics, and just an L filter or a C filter will not work, so we will have to have this combination. And finally, you can see that it is connecting to the grid, but through a transformer. So always a central inverters will need a transformer to connect to the grid. Because the transformer, the reason for having a transformer here is this inverter will have an output voltage of 4 400 or 480 or 580 AC, depending upon what DC we connect. But when the grid, usually these large systems, when it has 100 megawatts or 200 megawatt of installations, the grid will have like 33 kilovolt, 66 kilovolt, 11 kilovolt, or even in some countries like Indonesia, it's like 150 kilovolt. So it depends upon what the grid voltage is about, and then the step-up transformer is used to convert the voltage or step up the voltage to the grid's level. And within the box, you can see a lot of control functions, which is grid synchronization, which I explained earlier, the DC link voltage, current and voltage control, because you need to control both the current and the voltage. There is one more function called MPPT, which is called maximum power point tracking. The subject itself is too big because MPPT itself is a very big topic. But in short, the purpose of MPPT is, imagine that you have a solar panel and there is a cloud passing by, and then the irradiance level falling on the solar panel reduces. So what happens is, the output of the inverter, I mean the power output of the inverter connected to the grid, will always vary with respect to the irradiance level falling on the module, on the PV module. So there is an algorithm run on these inverters which will constantly see what is my previously generated power. For example, if it is a 1 megawatt system, it will see, okay, I was generating 600 kilowatt now, and next, what is my generation? If it is going to have 610 megawatt, the MPPT algorithm will tune the voltage accordingly. It will tell that, okay, the voltage is going in the right way. And if the 610 megawatt is going to go to 650 megawatt, fine. In the same profile, the MPPT will keep tuning the voltage. But when the 650 megawatt, for the reason of cloud coverage, suddenly falls to 600 or 550 megawatt, then the voltage will be adjusted within the inverter level, because the current is not in our control. Current is in the control of the sun. Directly, the sun's irradiation is directly proportional to the output current from the PV module, but the voltage is always in the control of the inverter, because we can switch and we can alter that. So the voltage is changed, and then the power will be tried to kept at the maximum at all point of time. So that's the reason we call that as maximum power point tracking. That's an algorithm. And then we have other auxiliary functions, and then you can see there is a SCADA, that is a supervisory control, which is usually we call that as SCADA, supervisory control and data acquisition, that is coming from the distribution service organization or transmission service organization. In our case, we can call that as our TNEB or KSEB, depend upon whichever state we are working on. And it is also, you can see there is a communication layer which is showing the symbol of an Wi-Fi. So all these data are then transmitted to a cloud, and then I will tell why, I mean, we are collecting all the information. I have a slide at the last to explain about that. Similarly, we have this wind systems. Wind, you can see that there is a wind turbine, and then it's connected to the gearbox, and there is a double fed induction generator, and it also has all the protection and things like that. But inside the wind power converter, what we have is nothing other than power electronic switches. So you can see in all the power systems, including solar, wind, and hydro, energy storage, whatever you take, power electronics plays a very prominent role. And a typical power block, so we have been only seeing the power blocks, but this is the actual photograph of one of the inverters. And this is how the inverters look like. You can see that, I'll try to show the names of this. Okay. Well, so you can see that from the bottom, if you see, there are fuses. So when DC is coming, or when even imagine that this is a wind power converter. So when the power is coming from the inverter, it needs to be from the generator, it needs to be protected with the fuses, and through the line reactor, it goes to the converter. The converter is basically, here is a frequency converter, because it need to also get synchronized with the grid whenever there is a change in speed and torque in the wind turbine. And there is a capacitor filters, then it goes to individual power blocks to ultimately connect it back to the grid. Well, now let's see some of the integration concepts. So we were only talking about the individual solar or wind or things like that. So how to interconnect two power systems and what role the power electronics plays here. You can see that there is a grid, and the PCC is nothing but the point of common coupling, and then there is a switch which is then disconnecting or connecting to the loads, AC loads. So this is how our traditional system in our home is looking like. What we can do here is, you can connect a solar system, you can connect a solar panel, and then the D2A is nothing but DC to AC. The solar panel's DC power is connected to the AC power, and then it can also get combined to the traditional grid and it can work together. So here the DC to AC is nothing but our photovoltaic inverters. We can also couple a battery with a bidirectional DC to AC device, and then we can use in the same network. So what is the advantage in this particular system? When the PV is not available, the excess energy during the daytime will be stored inside the battery, and we can use the battery's energy or battery's power to the loads whenever there is no PV or even whenever there is no grid. So that's one more application in the schematic. And imagine that you have some DC loads as well. So we know that there are a lot of telecommunication systems that needs only the DC load. So there will be DC SMPS, there will be a DC converter, and it needs only a DC power. It doesn't need an AC power. So in that case, what we do, we can connect the similar system, and then we can directly provide that to the DC loads without the requirement of the DC to AC conversion. So there are a lot of power electronic topologies available, and it purely depends upon what type of application we need and what capacity or what kilowatt or kVA of loads that we have. Accordingly, we select the power electronic components. And this system, you can see that typically this is used in some of the factories. So you can see the load at the bottom. That's nothing but there's an RLC load. We call that as resistive, inductive, and capacitive, because the load is usually RLC. When we have huge motors in the industries, there is an inductive load. There are some capacitive loads as well. There are some resistive loads like lighting and things like that. So it's a combination of loads. When the grid is connected to the transformer and through the switch is coming to the loads, you can see that whatever I explained earlier, this is a larger system. A PV and battery can be combined, and between the PV there is a switch. That's nothing but a PV inverter. That's a power electronic. And you can see there is a battery. One difference you can see from here, near to the PV there is one arrow that's only showing the one direction of power flow, because the PV modules are generating. The DC is converted to AC, and the AC is flowing to the grid. But in the battery configuration, you can see that the arrow is marked in both the sides, which means the battery DC can be converted with a battery inverter to AC. At the same time, when we have a need to charge the batteries, we can pull the power back from the grid or back from the PV to charge the batteries, which means it is a bidirectional architecture. That's very important to understand the difference. So we use the same switch, same IGBTs, same capacitors and everything, but the way we use the network is like, here it is a bidirectional and there it is a unidirectional. And the control system plays a major part here in taking care of whenever there is a switching between the direction of power flow, nothing happens to the system. So that's one interesting concept. Why we use this kind of system? So you can see that the load is marked in a dotted line. Yeah, the load profile is maybe like you can see in 2 time zones of a day, you can see the power of the load is reaching to the top, which means like, just imagine this is a home. In our home, morning before we leave to office, we use most of the electrical equipments are load, and that's why we have a peak in the morning, and we go to the office or college, and then there is a drop down on the load requirement, and again in the evening when we come back there is a shoot up. So for this kind of systems, what we can do, wherever I'm showing as the red here, the batteries can get charged from the grid or from the solar, because the load is less, and what are we going to do with the excess energy? So we don't want to waste that, so we can charge the batteries, and we can use the batteries to discharge it to the same load in a different time zone. So this application we call as peak shifting or energy shifting. So nothing but we are shifting the energy from one point of time and using it to the another point of time. In this system, the benefits are, you don't want to upgrade your transmission system, just that you have a 500 kilowatt of load as per this graph, just that you have a 500 kilowatt of load for a very short period of time in a day. We don't want to increase the substations, the transformers, the transmission lines to 500 kilowatt, right? We can have everything designed for 300 kilowatt, and we can only, we can use the battery to compensate that excess need in the load. Yeah, and here you can see again power electronics is having a major role. One important thing I would like to also show you here is that you can see that there is a battery and there is a IGBT with a back diode, and then it is switching and it's giving the AC, it's connecting to the grid. But recently there has been an advancement that even without the grid, when there is a grid outage, you can see the SS, the switch SS is open. When there is no grid, we can make the battery and solar system as a virtual generator, right? We can, it's an important word, it's a virtual generator, which means that we can have the kind of micro grid within our home, within our office, within our college, within our community, within our village, okay, even within a power system. So we have done a similar type of projects in many parts of the world, particularly in islands. So when there is a completely grid outage, we open up the grid switch and then we form a microgrid and we activate all the components, all the equipments within our renewable assets. And that's where the complex power electronic control system comes into play. And that's what we call as VSG, virtual synchronous generator. So it will be able to maintain the voltage when there is no grid. The battery inverter will be able to maintain the voltage to 230 or 440 if it is a single phase and three phase particularly, and it will be able to maintain the frequency at 50 Hertz, and only the current to the load will depend upon our source. When the source of the solar is higher, we will be able to get high current. When the battery is fully in a charged stage, we will be able to utilize the high current. So otherwise the voltage and frequency, the phase rotations and everything is undisturbed in the whole system. This is really gaining a great advantage in the global market, particularly in the renewable space. So grid is nothing but a synchronous generator, an actual synchronous generator, right? I'm just implicating, it's not a generator. It doesn't mean that grid is having huge generators at the back, but grid is acting as a synchronous generator. But this kind of systems, what you see here is a virtual synchronous generator. It doesn't have any rotation parts, right? It doesn't have any rotation parts. The inverter doesn't have a rotation part. The battery doesn't have a rotating part, but it can still do the purpose of the generator. That's more important here. Well, we have also tested this kind of system. So this shows some of the actual images showing how we parallel up. That's what we call as black start. So black start is like when we have a complete blackout at the grid side, but still with the renewable assets, we want to charge the grid. It is called as black start. We can also do power sharing. When we have higher loads, we can couple multiple of these units in parallel, and we can do that. And the most important thing is that you read the last point, it's a seamless power mode switching, which means that when we do this switching from the grid to the renewable asset, you will not even know that this happened, which means there will not be a flicker in the light. When you even work in your computer, the computer will be uninterrupted. There is a completely seamless mode of switching, which in practical we have seen it took like 20 milliseconds to switch over from this power to the renewable power, which is fine for all the critical equipments, even some of the data center equipments. So let's talk something about the power electronic control system. What is the requirement and what main things that because the power electronics and control systems are always integrated. We cannot have an IGBT and diode or an MOSFET just working by itself. We obviously need a control system. It could be an it could be an IC, or it could be an controller, whatever sort it could be, but we need a controller to control it. So Power electronic and control system goes hand in hand. What it needs to do whenever we are connecting a renewable energy asset or a renewable source to the grid or to the load, we need to take care of the reactive power and power factor requirements. We need the power to be clean because we don't want to inject any harmonics. And the grid connection transient. So we will always have the power requirements or the curve going up and down. We will have to minimize that transients. And okay, so let me touch something about this. I think you all know about this, like the phase lock loop. This is one of the control functions. So the PLL is one of the main control functions in the inverters, particularly because it needs to deal with the unbalance whenever there is a negative sequence voltage. So what happens here? We have a source, here we have the grid to deliver, and when we have multiple of the sources, there is a huge amount of negative sequence voltage and positive sequence voltage impacting, and the control system has to be rightly designed, and particularly the phase lock loop is very important for that, to make the inverter synchronized with the grid and maintain the three-phase voltage and frequencies. Another important control system in power electronic is the voltage control block. So all these are whatever I'm showing here. These are all taken from the actual product reference, not from academics. So this is what we are using in our day-to-day life in designing a product and utilizing a product. So you can see there is a great amount of overlapping whatever you see in your books and in the industrial utilization in actuals. So the voltage control block is nothing but, so there is a VDC demand. VDC is the voltage of the DC. The VDC demand is set inside the inverter. That's what you can refer this to the MPPT as well. So we can define here, I need a 600 volt demand, but when the actual voltage is coming like 500, 580, whatever it is, then we use a PID controller, a proportional, integral and derivative controller, to get the system's feedback and correct it with our algorithms. Okay, this is the most important, one of the most important. So you can see we have the inverters, we know the inverters, power electronics, but we cannot connect that to the grid. I told you about using the LCL filter. Sometimes even the C has a R because the R is a damping resistor here. So the reason being, whenever we are charging the capacitors for the first time, it could take up a huge inrush current, and we need to have some damping resistors for smoothly charging the capacitor. So that's why you see an R here. And with this setup, we can have the grid to have a cleaner power with lesser harmonic and with lesser turbulence. So that's why we have this control system also. Okay, so this is what we call as island control or grid forming control. The one, if you remember, I was telling about the virtual synchronous generator. This is also known as grid forming. So which means there is no grid, but the power electronics and control system can form its own grid. This is not just in the scale of 1 kilowatt and 2 kilowatt. We have did projects with 10 megawatts and 30 megawatts with grid forming. So there is a huge township, and the huge township is just working with grid forming inverters alone. I mean a 30 megawatt of inverters, all connected in parallel. So the key points here to note is that it should have the black start ability. So which means the inverter, imagine that there are so many, PV modules connected to the PV inverters, but then you have a lot of transformers at the load side. So whenever we are charging the transformers, it will take an inrush current, right? Because we are charging the transformer from the secondary side. Usually the transformer's primary is connected to the grid side and secondary is connected to the inverter side. When we are using a grid forming mode, the primary side of the transformer is already off, right? It is not induced because the grid is off. So we are charging the transformer from the secondary, and then we are charging through the secondary, the transformer's primary side is getting charged, and then from the primary side of the transformer, it's flowing to all the load networks. So here the black start ability means that a smooth starting, a step starting of the transformer. So a small concept. So what is an inrush? Why there should be an inrush current in a system? The only reason for the main reason for the inrush current is there is a variation in the voltage, or there is a difference in voltage. When there is the same voltage, there is no requirement of inrush current. So what we do here is that we don't allow the secondary of the transformer's voltage to vary frequently or very suddenly. We just vary that step by step with the control algorithm, and then the current inrush also happens in a minimal proportion, so we don't have any problem in the whole system. The system works fine without tripping. And that gives some of the data. Well, okay, this is one more interesting concept, anti-islanding protection. Islanding and anti-islanding. So let me explain this. Islanding, you can relate to your virtual synchronous generator or grid forming, or islanding is all of the same meaning, which means that we are completely disconnected. It's like an island. Island is disconnected from the mainland. Similarly, an island network is completely disconnected from the main grid, and we are using all our available renewable sources to connect and getting utilized within the load networks within the island. It doesn't mean it is an actual island like an Andaman or an Maldives, but I'm telling that island is just disconnected from the grid, but it is available, very much available. It could be anywhere in Chennai as well. A particular portion in Chennai as well can act as an island with respect to the power. But what is anti-islanding? Why an anti-islanding protection is required? Well, imagine that an inverter is having the capability to pump the power back to the grid when there is no grid. So our TNEB friends might have switched off the circuit breaker, and they will be doing something on the power network flow. But here and connect it back to the grid, what will happen? It's going to be a fatal accident, right? Because the power is going to flow, and whoever is going to work in the network is going to be electrocuted. That's why in some of the systems, so wherever the island function is not approved, we should have anti-islanding protection, which means the inverter, a part of the inverter's control system, should detect the failure of the grid. Within no time, it should disconnect itself from giving the power back to the grid. So there are two systems, so please don't get confused here. One is the anti-islanding protection. Whenever we are working in a mainland grid, we should not pump the power back to the mains without any permission from the grid. And when the system is designed for an island protection, like we have did projects in Andaman Island. So there they tell that, okay, if the grid is off, you can open the circuit breaker and you can form an island with your grid. So, I mean, with your inverter. So it depends upon the authority's approval. We can do both the functions, and the control system is largely varying between these two applications. So this particular graph is a real life graph made for 100 kilovolt load testing. You can see that there is a load imposed, which means the load is applied. You can see the graphs here, the current and voltage waveforms at the bottom. You can see whatever happens when the load is applied. And then what we have done is that the virtual synchronous generator, I mean the inverters are shut down, right? The inverter which was supplying, when I say inverter, it's a solar inverter, it's a renewable inverter. That's shut down. So when the inverters are shut down, you can see the profile changing, and the VSGs2 restart, which means that after switching it off, you can see that in between the green is started, right? So we can see the grid is getting connected again, connect to the grid, and the demand dispatch is completed. So grid support, and then disconnect from the grid. So what I'm trying to explain from here is that when we are connecting to the grid and when we are disconnecting to the grid, the load doesn't suffer any problem. The load is as it is. It doesn't shut down. It doesn't take a dip. So with the help of these inverters, with the help of our power electronic advancements, irrespective of the grid coming and going back, we can have the electrical networks unaffected, and it could work seamlessly without any problem. That's what this is trying to explain. This is a similar graph of both voltage and current. And this particular graph is like when we have 4 inverters in parallel, because we need more power. So when we need 400 megawatt of power, but when we have only 100 megawatts of or even like kilowatts of inverters, we need to parallel them everything, and we need to take care that all of them are working in a synchronized way, and all of them are delivering the power in the same profile and same sinusoidal waveforms. So again, the control system is very tightly coordinated between all of them. You can see the graphs are pretty much overlapping, and between the inverters, when I say the graphs, you can see all the I1, I2, I3, I4 are different, coming from different inverters, but still they are all overlapping with each. One is the current graph, and another is the voltage. So you can see the voltage is always sinusoidal, but the load, you can see it's not sinusoidal, because whenever you are switching on the load or increasing the load or decreasing the load, the waveform varies. Well, okay, we have, I think, gone through the power electronics, and then the different type of renewable assets and the use of power electronics in all of them. But then let's now go towards the monitoring, the control, and the fancy word of artificial intelligence or machine learning or whatever it is. So how are we going to take the data from the system? So you can see there is an inverter, there is a power electronics that you see in the left hand side. And then there are multiple of communication methodologies. Like today I'm talking in English with you and you are understanding that. But if somebody is talking Spanish to me, I might not understand. So which means the communication is not happening between a person to person. So there is something called protocol. Here in human language, we call the language as the protocol. When I speak in Tamil and you understand, so the protocol is Tamil. So both of us understand. And when similarly, if I speak in English, I'm using English protocol. But between the components, between the equipments, also there is something called a language, which we call as protocol. So what you see here in this drawing is one of the protocols that's called as Modbus RTU, remote terminal unit. There are multiple of protocols. There are Profibus, there are DeviceNet, CanOpen, CAN bus, Genius bus, Ethernet. So all are communication protocols, but we pick up the communication based on certain requirements, like based on the distance between two equipments. Is it like 1 meter or is it like 1 kilometer? And then the baud rate, you know, the rate of data transfer or bits transfer per second. And then number of devices connected in the whole network. Is there just 3 networks, or is there just 3 nodes? We call that as nodes. Or is there like 1,000 nodes? There are also 1,000, 2,000 nodes in certain networks. So when the number of nodes change, the ability of the communication protocol should also help the network communicate properly without getting delayed, without getting shutting down, without transferring a wrong data. So that's a glimpse about the communication. And you can see there is Modbus RTU, and then you can ask why there is an HTTP coming to the web server. That is a different protocol. So that could be one of the questions from this slide. But you can also see a component which is nothing but that's a communication converter. So in market, we also use something called communication converter, which is similar to our Google Translator. So I can type your language and then I can understand what you are speaking. So similarly, we also use communication converters or protocol converters because these components are used in different countries, and different manufacturers have their own protocol. So we will ensure that the communication converters are available to map and match all the communications that we do. So the purpose of this slide is, you can see that from the inverters, from the renewable assets, we pull a lot of data into this network. A lot of real-time data and historic data, we will be pulling it out. And then we will be storing it in the cloud and using it for another purpose. So why we do that? We know that anything in control systems, we know the best control system is something that is having a feedback, right? A network without a feedback will not do anything. And what are we going to do with the feedback? We are going to read the feedback, analyze the feedback, and then act upon the feedback, right? And only then we will be improvising. Very similarly, why we take this data? First, we collect the data, or we accumulate the data, we store all this data, and then we analyze the data, and then we use that to improvise the whole system. Let me tell you some examples. And this is where we are shifting towards our next topic of machine learning. You have, let me tell a real life example. So we all have our mobile phones, and the mobile phone, probably some of the mobile phones in the future will have a machine learning in it, which means that it will monitor the battery life, whether it is 20% or 30% or 100%. It will monitor the load. The load is like how many applications that you are using in parallel. You might be using a video file, a video call, an audio, whatever it is. So the more applications that you run, it's going to load the equipments or the components of the mobile, which means the current consumption of the mobile is going to be higher, right? So you're monitoring the battery life, the battery percentage, the application or the load that you are using, and then the ambient temperature, because it also depends on the power derating of the component. So at what temperature the phone is now. With these three data, the mobile knows that this is how my processor speed should be. It could be like 1 millisecond. If at these conditions, right, when you are loading your phone to 80%, when your battery charge is at 50%, when your temperature is like 24 degrees, my processing speed will be acting like 1 milliseconds. But when you're in the same conditions, when you are processing, when your loading goes to 100%, you are simultaneously using a more application to it. Eventually, what will happen? Your processing time. Sometimes that you will feel that, okay, I'm clicking this app, it's not opening. I'm opening this video, it's not opening up. So what will happen? The machine will learn all of this, and it will find out what is a nominal application or what is the nominal use case of this phone. And then it will be giving all this data to the manufacturer, because the manufacturer has the control on our device, right? So he can tell us, you upgrade the firmware and I will make your phone better. So when you are upgrading the firmware, you are giving permission to access all your data. So what that guy will do with you, he will analyze all the data, and then he will make an algorithm, and then he will tune it. He will tune the machine, and the machine will learn and it will act upon. So next time what it will do, it will prompt you to do something. So your phone is overloaded, can you please shut down some of the application? Your memory is full, can you clear some of these things? So this is one real life example I'm giving. This is nothing but it's a machine learning, which means the human, we are not teaching the machine, right? We are not telling the machine is learning by itself, and it is correcting by itself. In energy systems, let's see in energy systems what happens. The purpose of having the machine learning in energy systems is nothing but it should read the data, it should analyze the data, and it should correct it for the betterment of everybody. So you can see one of the curves here at the top. Usually in a renewable form in real life, we have something called a forecast power or a kind of guaranteed power that we have to provide to the network. So when we have a renewable asset, renewable farm, when I'm connecting it to the PGCIL or NTPC, so they will be telling that, look, okay, you are connecting your power to the grid, but tomorrow I will need this much of megawatt. And if you are going to fail, I'm going to put you some penalties. That is how particularly the wind networks work, because based on our based on the owner's acceptance, there is a power purchase agreement is made between the user and the government will know that, okay, today this guy is going to give me this much of power, and I can plan my another assets depending upon that. And if I'm going to fail by not providing him this power, then there is going to be a collapse in the grid. So that's the reason we have to respect the forecast, whatever we have provided. And what machine learning does here, it will collect a huge amount of data again, including the meteorological status, like what is the wind speed, what is the ambient temperature, what is the pressure, what is the humidity, and with all these conditions, what is happening inside my inverter. So what is the switching frequency of the inverter, what is the temperature of the IGBTs, whether my capacitor is, whether my cooling fans are properly working. So it will monitor all the data, and then if there should be a problem, if it will identify in this condition, I will not be able to deliver the power of X megawatt tomorrow to the grid. It will identify by itself. And it will also see the weather forecast, because we have something called weather stations, pyronometers and things like that we install in the farms, when I say farm, wind farm or solar farm. It will tell the futuristic data as well, and it will tell that, okay, with all the data that I have acquired, I am very sure that I'm not going to respect that forecasted power. So what I will do, I will either intimate the grid in advance that I have some problem, I will need something, so that my penalty can be saved, or I can put on some alternative resources, like I can pull on a diesel generator or something only for that period of time to cope up the power. So I don't have more slides on machine learning, because we are working on a lot of research currently, and I cannot unfortunately include some companies' information. But I want you to get an overview about machine learning. Is not just fancy, it is already implemented in most of our real life systems, and it's already getting implemented in most of the renewable energy assets like wind and solar, as I was telling, and it will continue to grow in a vast proportion. So I think I'm 5 minutes ahead of time, so I will stop here for any questions that you might all have. Thanks for the time. I'll wait for your questions.
Thank you, sir, for sharing your deep knowledge with us. Today's lecture was full of knowledge and thought-provoking address. Participant may now ask your queries. Otherwise, kindly post the queries in the chat box.
Okay, I read that. Kindly tell the viability implications. Okay.
Sir, may I read the queries?
Yes, ma'am, please.
First question is Sandeep Chaudhary. He has asked that peak shifting, battery charging coordination, which algorithms are preferred? This is one other question.
Okay, in peak shifting, which algorithm? So, okay, algorithm by name, or because what we use is a programming that doesn't have a specific name to it, but what we use is basically we put a block and then we define at what time. It is a kind of comparator, and then a real-time monitoring. So it will see at what point of time what power we need, and then it will switch to that block and work by itself. So there is no dedicated algorithm probably, but then it's a customized, whatever we use in industrial is all customized algorithm. So it doesn't have a name, to be frank.
So another question is asked from Ramesh Jairaman. What is the significance of reinforcement learning?
I think his question is about machine learning. So that's always better, because the more learning or the more data or whatever we learn, whether we are going to repeat the same data pool again, and then analyze it and then take it back. So it's always going to be better. So today, in most of the equipments, in most of the devices, this machine learning is still in an R&D stage, I would say. So none of us or none of the renewables assets have come up saying that this is the best system. So we are evolving, and then we will eventually continue to improvise on this system, sir.
And then Manikandan sir has asked, any specific tools or software needed for machine learning?
Of course, yeah, there are a lot of tools required, primarily to use. There is I think you are aware about Python. It's one of the simplest tool, I would say, because Python can handle a huge data, I mean a large data or a big data, and then we can simply program that to get our results whatever we wanted. Otherwise, without any tool, it's impossible to do this kind of applications.
No more questions in the chat box. What is the That is, what is the importance is L2 regularization?
Okay,
What is the importance is?
I think Samrat's question is about L2 is the filter number 2, that is the inductance 2. When we are using an LCL filter, the first filter we call as L1 and second filter we call as L2 and in between C. So the importance of L2 is depending upon the harmonics and the switching frequency, whether we need that or not, because in the first filter we mitigate like the L2 is important because from the grid side we will be having like 6% harmonics, and the free motor side will be having 3% harmonics. So L2 is actually important to have this kind of harmonic mitigation for sure, particularly depending upon the switching frequency of the power electronics device.
Yes, no more questions. Any questions? Participants are requested to post your queries in the chat box. Mohammed sir, shall we analyze the switching surges with machine learning?
Okay, switching surges with machine learning, not at the device end, but at the output end it's possible. Because why I am saying not at the device end, machine learning will need data to be pulled out from the devices. Within the devices, currently we do not have any of the communication integrated. For example, if you take an MOSFET or an IGBT, we do not have a communication system embedded to the switch itself. But yes, at the output, we have the CTs, basically the current transformers, sensors, which take these surges, and we shall for sure analyze that.
So, participant, kindly post your queries in the chat box.
Sir, one more question, sir. I'm from Manigandan from JCT College of Engineering Technology.
Yes, Manigandan, go ahead, please.
Yes, sir. Why we can adopt for AI techniques, sir? Possible to adapt the AI techniques in for renewable energy sources, artificial intelligence techniques.
Yeah, there is.
You can say machine learning concept. Okay, if it is possible to adopt AI technique in renewable energy systems.
AI is, I would say that, of course, there is a very thin line of difference between AI and ML when it comes to the renewable systems, because there is already an artificial intelligence implemented. I will tell you why. So you take the solar inverter, it will start by itself in the morning. When the sun is rising, there is no operator in the field. I'm talking about the larger farms like 100 megawatt, 200 megawatt, even 10 megawatt. So there is nobody on field. So with the artificial intelligence, which means by the azimuth angle and zenith angle of the sun, it will wake up by itself, and then between the daytime with the irradiation level, it will work on the MPPT algorithm, and when the sun set after 6, it will shut down by itself. So that is a kind of artificial intelligence already getting implemented. But what I'm calling as a machine learning is that what we have not done so far, we started to pick up the data from all these machines, and then we study that, and then we work on improvising that. So your question is right, Manigandan, but it's a little bit of terminology difference that how we are seeing things.
Thank you, sir. Thank you so much.
Yeah.
Any further queries? Any queries? Any queries from participant? Yes, now we have come towards the end of the event with the appreciation and the gratitude to all those who make this event a grand success. On behalf of EEE Department of Ishwari Engineering College, it's my privilege to propose a vote of thanks on this occasion. I would like to thank the chief guest of today's session, Sivaguru Paramasivam, energy storage expert. We are really enlightening us with their commendable subject knowledge on application of power electronics and machine learning to renewable energy. I would like to thank the chief guest who gave his vital time from his busy schedule to grace this meeting. Thank you, sir. Our sincere thanks to respected chairman sir, co-chairman sir for giving this opportunity. I would like to thank our principal sir for his continuous motivation. We are also thank to our HOD sir for his continuous support for making this program a grand success. I thank you all for clearing the doubt and enhancing the conceptual understanding towards recent advancement in electrical engineering. Thank you all once again for giving us your precious time.
Thank you, madam, and thank you everyone, participants, for your time. Thank you. Have a nice day.
Thank you, sir. Thank you, sir.
Bye.
Feedback link is posted in the chat box. Feedback link is posted in the chat box. Tomorrow, I request all of you to join the FTP through Google Meet sharply at 3:45 p.m. Kindly join us. Thank you. Those who have completed the feedback, you can leave the meet. those who